Okay, so we'll do this as 2 recordings. So obviously we'll do another lunch break around 11:30, and then after that we'll do more lab stuff. So the first thing I want to do is go over the Google form with you guys and take a look at the responses. We'll keep the responses anonymous, so you'll probably be able to recognize your response. And the responses look pretty good. Some were kind of funny. So let me pull them up here. So first of all, here are the questions. And so it looks like everyone responded, which is great. So the questions were, in your own words, what do you think, okay, that's a typo. What do you think the subject, no, it's not a typo. What do you think the subject of physics is truly studying? So let's look at the responses for that. And we'll kind of look at each one and kind of talk about, about each one. So I feel like physics subject both movement and calculating and movement created. Totally agree. It's huge on movement, especially for the first quarter, first semester of physics, of college level physics. When you start getting into electricity and magnetism, it gets a little bit more. Oh, I need to share my screen. Here we go. Okay, much better. All right, Jonathan, you're here. Great. Okay, so everyone is here. Okay. So yeah, I feel like physics is subject of both movement and the calculating of movement created. Totally agree. Especially all the stuff we're doing in this summer. But when you get to the more abstract stuff like electricity and magnetism, there is movement. You're looking at movement of like electrons and charges. It's just hard to visualize, but that is really what it is. So that's great. It's an independent approach to understand reality, motion. Mm-hmm. There's really ooh, I like that one. Mathematical and logical undertakings. Absolutely. It's a very mathematical science, probably the most mathematical of all the sciences. Logic is obviously kind of a big deal for all of them, but definitely a big deal in physics. Physics, in essence, works to explain the complexity within our universe and tackle aspects that we don't really think about, such as speed. Okay, great. Wow. These are aspects that are natural and occur without us necessarily doing anything. And physics works to unravel these. That's impressive. I like that one a lot. Physics' use of math to explain describe phenomena, good, occurring as well as structure of the universe. Mm-hmm. Studying nature, why things happen the way they do. So physics allows people to better understand the nature of reality or the phenomena of the universe, mm-hmm, using foundation mathematics. It seems to be studying the laws and states of the earth while also analyzing motion. Mm-hmm. Study things that exist, mostly the way they interact with the earth. Absolutely, we're going to do a lot of, like gravity, for example, is interaction with the earth, right? Because we're looking at things falling to the center. And the acceleration due to gravity is 9.8 meters per second squared. So we are going to use that a lot, especially all these things here. Matter, mm-hmm, mm-hmm. Motion, mm-hmm. Everyday actions will be precise, understanding them for our advantage. Yes, we definitely want to use physics for our advantage. Physics is used, right now, like how we're on this computer and doing this, it's all physics, right? All the electronics that we work with. Mm. Mm-hmm. Complex phenomena and common stuff. Mm-hmm. Good, great. So you guys did great with that question. All good responses here. Vector and scalar. So vector, remember, involves direction. Scale does not. So that's what I'm really looking for. Mm-hmm. Yep. And just so you know, speed is scalar, velocity is vector, distance is scalar, displacement is vector. We're going to be talking a lot about that today. Mm-hmm. Yep, all looks good. You guys are getting it. Great. Reference frame is more like how you are kind of like seeing something. Like obviously if you're driving in a car and you see another car driving right by you, it looks like that other car is motionless, but you guys are obviously both moving. So it's about observation points of view. Mm-hmm. Mm-hmm. Let's look at this one here. I like the example. A point of view from which you are measuring things. Now, if you're in a plane with zero turbulence, it can feel as if you're completely still. If you look at the ground from your point of view, it could look like the ground is moving. As a valid point, no matter what is actually moving, because the point of view that, if you're like at the control tower at the airport, I mean, those planes are moving fast, right? But for example, does anyone live in Millbrae or up in the hills in Burlingame or no? Okay, well, I used to tutor someone in Millbrae, RAP 280, and you could see I just get so distracted. You see all the planes landing and taking off from SFO. It happens actually every minute, but that's my reference, right? My frame of reference, where I've seen these little objects come down like kind of slowly, but if I was up close, it would look a lot faster. If you're on the plane itself, it's different as well. So 68 miles per hour in the conversions, good. This one's a little bit incorrect, so I think you may have just accidentally divided by 4, so be careful for that one. So this is kind of funny. I like this one. Whoever.
Mr. Moshny?
Yeah.
That last problem, how many sig figs were
Oh, great question. Actually, because you're dividing, you're only going to do 1 sig fig, actually. So we should have said 70 miles per hour. I didn't ask you to. Yeah, because 5 is only 1 sig fig.
So, and then how about for the second part of the problem?
Should be 1 sig fig also. Yeah. Should have been 70 and 30. You know what I'm going to do, to be honest with you guys? I'll just tell you guys what to round to, so you don't have to worry about it. Don't worry about it. I'll just tell you what to round to. Like on the test method, say just round 2 decimal places. So I don't want you guys sweating it. First, I probably should have done 5.0 hours. So that way, because I think 68 is better to know than 70, especially when you're dealing with like speed limits, because that could make or break whether you get a ticket or not. So yeah. Especially because the speed limit is like 65 miles per hour on the freeway. So it's kind of good to know, like if you can get down to Union's place. I'm looking forward to more talk of Velocity Grad because I think it would be dope to become a pilot. I like that. Not sure if it's pilot for a commercial airlines or Air Force pilot. When I was really young, that's when the movie Top Gun came out and everyone wanted to be a jet fighter. So sharpen my mind. Yeah, actually, we are going to do some stuff that's a little bit doing with calculus today. So pre-calculus BC honors. So you're probably moving on to AP calculus next year. I know some of you are only moving on to pre-cal next year, so you're a year away from calculus. But there's calculus and physics are very intertwined, and I'm going to do actually a little calculus for you guys today, believe it or not. So we are going to do a little activity on that. All good stuff. Okay, great. So were there any other questions about these Google form questions before we move forward? Oh, okay. If we look at the discussion topic, and it's okay if you haven't done a post yet, but tomorrow morning I do want you to have at least your first post. But I'll have you do more reading and stuff on it tonight. And so if we look at week 1, and I already put the homework for tonight up here, so we'll talk about that as well. So make sure you keep, click on this link, read through the other lessons here, and then you should be able to answer. And actually, you'll be able to answer these after today's class too, because we are going to talk about the slope of velocity time graphs. We are going to talk about what the area beneath the velocity time graph tells us. And then, you could describe any real life situation. You could talk about an airplane, talk about being in a car, talk about riding your bike, talk about just walking or running. All things that involve motion is kind of what I want you guys to share and discuss in this discussion board. So, but tomorrow morning, I want you guys to have your first post, even though this is not due till Friday. Maybe I'll change the deadline on that so you guys actually get a post in, and then we'll update that deadline so you at least respond to other posts by Friday then. And the homework that's going to be for tonight. Oh, and actually, really quickly, did this homework take anyone more than an hour and a half to do? If it did, please let me know. But if it was all under 90 minutes, is that fair to say this took less than 90 minutes to do? Yeah. Okay. So I'll try to keep that in place. So the homework then for tonight will be 4 more videos to watch from Khan Academy, dealing with motion and kinematics mainly. There'll be a new Google form to answer, and yeah, and the new Google form. Let's make sure the link works. Yeah, okay. And yeah, continue reading, and then we're going to be working these worksheets today. Okay, so if there are no more questions, we could probably get a head start on finish up 1.3, and then I'll also do a lesson on 1.4, and then I'm going to give you guys a chance. So probably I'll need about maybe 25, like maybe till about 10:40, 10:45. I'm going to do a little lecture. Then I'm going to have you guys do problems on 1 through 1.4 for till about 11:15, 11:20. I'm also going to do a little demonstration with you guys as well. That's a really kind of neat demonstration. And we are going to start working on the lab after lunch today as well. Okay, so let me pull this up. So if you guys want to get the problem set packets out, the one that says week 1. Let's see your problem sets. And we're going to work on velocity and graphs again. So we did do all this stuff here, but let's actually talk about, I think we did 3, 4, 6, 7. So let's talk about 1 to 5, and then I'll have you guys then do 8, 9, 10, 11 after that. Okay, so let me expand this just a tad and pull up my stylus here. Okay, so what is the meaning of obtaining a negative velocity? So remember what velocity is. It's the displacement over time, or it's a change in position over time. Now, how do you define position? It's all up to you, actually. Position could be, let's say, defined as the miles from San Francisco. So let's say initially you're in San Jose. And let's say finally you get to, say, San Mateo. Well, San Mateo is closer to San Francisco than San Jose. So let's say San Jose is like 30 miles. No, it's more. I think it's like more like 40. And let's say San Mateo is 20 miles. And let's say it takes you, let's say you hit a lot of traffic. Let's say it takes you 1 hour. I've had that happen. Actually, I've seen worse. So your final is 20. Initial is 40. So that's a negative velocity. So what's the meaning of obtaining negative velocity? I would say all depends on how you define position. And we need final position to be less than the initial position. That's how you would get a negative velocity. So it's a lot of it is depending on how you establish the problem. And that's what physics is really a big part of. How are you defining the problem? And so that's, that's why you can't take a formulaic approach. You really have to make sure you have a clear understanding of what these things are, and then define it how you want to define it. If you want to define it as, the distance from another city, great, you can do that. But it all depends on how you define it. So hopefully that makes sense. Can I clear this? Yeah, okay. All right, so we'll go and clear that. Okay, number 2. Draw a quick sketch position and time graph of a ball being thrown up. So it comes down, so it goes up and then comes back down. Describe the graph using mathematical terms. Okay, so call this position and time. And so you throw the ball, so here's a person. Throw the ball up and comes back down. So let's say we define this as the distance off the ground. So say, for example, you initially have the ball. Well, if you think about it, we'll do this in feet, by the way. We'll do this in seconds. Kind of do a rough estimate here. And let me change the colors here. Let's say this is like 5, 10, 15, and 20. So I'm actually being a little more detailed. Now, when I throw the ball, how high? I mean, I'm about, like 5'8", 5'9". Initially, what do you think the height will be of the ball off the ground? Do you think it'll be 0 or maybe something else? Going on?
Should be like your height, right?
Yeah, roughly about my height. Depends where it releases from my arm. I mean, maybe like maybe I throw it really high, or maybe I kind of just start in the middle and throw it up. So I'll say 5 feet. Because 0 means that then I'm on the ground throwing it, which I could do that too if I wanted. But maybe we'll do that. And then it's going to hit a certain peak. Let's say I throw it pretty high up. Like, actually, I'll give you a great example. I was at the park yesterday with my family, and we saw these things called stomp rockets. And maybe I might actually get one and demonstrate for you guys. They're actually really cool, where you put a rocket and then you stomp on this little pad and it shoots the rocket up. But it hits a certain height. Maybe it's here after 1 second, here, and then it kind of then comes back down, right? And maybe after 4 seconds, it's going to hit the ground again, unless I catch it. But if I let it hit the ground, so you kind of expect something parabolic here. And then this is kind of open-ended. I mean, you could say a few things. You could say, for example, the vertex represents the max height. You could say the x-intercept represents the time it takes, or time the ball's in the air. So usually it's a good idea to focus on these 2 things. And also the y-intercept. What does my y-intercept represent, by the way? Anyone want to tell me what the y-intercept represents?
Initial position.
Yeah. Yep. So what you're doing now is you're now making a relationship between mathematical terms and physical terms. That's physics right there. You're connecting the math and the physical, right? This is precisely what we're doing. This is the whole point of physics. So number 2 is a fantastic question, especially part B. You learn all this stuff, x-intercept, y-intercept, y, vertex, blah, blah, blah. Now you're actually seeing how it's applied. And this is, we're just scratching the surface. There's going to be so many other great things we're going to do with this. So any questions about 2? Okay. Now let's take a look at 5. The difference between speed and velocity. Remember, we talked about the speed. Is just magnitude. Velocity is magnitude and direction. So, for example, say you're looking at, let's look at NASCAR. I'm not sure if anyone, does anyone follow NASCAR in this room? No? Okay. Well, because there haven't been many sports, I've actually been kind of looking at that a little bit more these days. But what is NASCAR, right? It's just, people in these race cars and they go around in a lap, right? Around a circle or oval, whatever you want to call it. So let me ask this question. Let's say a race car driver has a constant speed. Usually they're going to drive faster because they're trying to win a race. But when you get to the turns, you have to slow down. But let's just say he has a constant speed of 120 miles per hour on the track. So here's the car, and it's kind of going around the track. Now, is this velocity changing? Yes or no?
No.
Well, is his direction changing, though? Is it going in a straight path or a circular path?
No. It is.
Yeah, so in this case, the answer is yes. Constant speed, the velocity is not. And we're going to talk about circular motion, I think, in week 4. Okay. So now what we'll do, I'm going to have you guys go through 8, 9, 10, 11 in small groups. So we'll probably spend a few minutes on that. And then we're going to work on 1-4 afterwards. So let's go back to our breakout rooms. So you guys are going to be doing the last 4 problems of the 1-3 packet or 1-3 worksheet. Let's go breakout rooms. We'll do 4 here. Make them automatic. Okay, and we'll say we'll do this for 8 minutes is fine, 6 seconds. Okay. So I want you guys to try those, and I'll hop in to make sure you guys are doing okay on those 4 problems. I got an email with invoice. Do you want it? For the AC? I'll email you the invoice, okay? Oh, Chris?
Oh, sorry.
The invoice for the AC?
Yeah.
Yeah, I just received the invoice. I'll email it to you.
Well, that's the best one, which is long case.
Might be a slow, I can check it.
And then the full festival, we're supposed to be here between 9:30 and 10. We're
Okay.
still not here.
Okay, we're just waiting for some others to
So you called and texted?
And
get back.
so that's kind of.
No, I'm just gonna close the door. Okay, good. Everyone's back. So let's let me share my screen again. Any questions about 8, 9, 10, 11 that you guys wanted to share? Number 8, sure. So let's see here. How far in the future will this occur if the displacement to be made is 59 kilometers northwest, assuming the motion remains constant? So I do see a rate here that the land is moving at 6 centimeters per year. A little scary, but so the way I would set this up, excuse me, 6 centimeters. I would actually set up as a ratio. That's how I would do it. So it might be easier to actually convert maybe the kilometers to centimeter, or find a common unit to use. So maybe I'd change that to like 0.06 meters, because you have 100 centimeters for every meter, and change that to like maybe 590,000 meters. That way those units will cancel out. If you cross multiply 0.06x, and if you divide by 0.06, so I'll use my cell phone calculator. Yeah, and you get something that's close to 10 million. It's like 9833, but it rounds about 10 million. And you see 7 zeros, so that explains how you get that. And they did 1 sig fig, because you have 1 sig fig there. So that's how they got that. You could just, I would just set up as a proportion for that one. 9, 10, 11, any questions about those three before we move forward? No? Okay. So now you guys got that done. No question?
Can we go over 11?
Sure, of course.
That was rough.
Let's see. Oh, okay, it's dealing with circular motion somewhat. As Earth rotates around through one revolution, a person standing on the equator traces out a circular path whose radius is equal to the radius of the Earth. Fine. What was the average speed of this person in meters per second? Okay, so we want speed, right? We want the distance over time. Now, this person is covering a circular distance, right? What formula do we use for circular distance? You guys remember from geometry? What is that called when you're traveling a whole circular path?
Circumference?
Yes. What is formula for circumference?
2 pi r.
Yep. And that's your r. So that's what you're going to do. You're going to do 2 pi times 6.38 times 10 to the 6th power. This is where I might need to go grab my graphing calculator. And you're doing this. Okay, now we have to think about this also again. As Earth rotates through one revolution, well, how long do you think it takes to travel one revolution?
24 hours.
Actually, hold on a sec. Yeah, I maybe I'm thinking about whole. Yeah, no, you're right. Yeah, I was thinking like the when you go around like a whole, for a whole year, but that's something else. Yeah, I'm totally. Yeah, no, you're right. 24 hours. We probably want to convert that to seconds. So 1 hour is 3,600 seconds. So I'll need to kind of get rid of that. And if I do let's use a very typical calculator here. So if I do 24 times 3600, so it's 86. And then, excuse me. So 6.38 times 10 to the 6, that's 638. That's going to be 6,308,000. Sorry, yeah, 6,308,000. 2 pi is about 6.28, so times 6.28. And divide that by 86400. Yep, that's to get 464. And then the conversion you could do, do a Google search on that, or figure out how to go from miles and meters and then back to hours. So, yep, that's that one. Anything else on this one before we? So you had to assume some things, obviously. Assume a circular path, unless you're Kyrie Irving and you think it's flat. So, and of course, knowing that for a full day, right, we do rotation. Any other questions about these four before we move forward? No? Okay. So let's now look at 1.4. And we're going to start looking at graphs as well. And then this will be a nice segue to one of the activities we'll do. And then, of course, we'll do a lab. So let me share my screen again. Okay. So let's talk about acceleration now. So you hear the word accelerate often. What do you think of when you hear the word something's accelerating or even decelerating? Someone wants to chime in.
Like speed.
What's happening to speed if you're accelerating?
The speed changes.
How?
Like it either gets faster or slower.
So that'd be accelerating when it's faster, and then when it's slowing, you decelerate. So a thing like when you're driving a car. So this is actually a great question. Let's say I'm driving a car. Oh, come on. There we go. And I slam the brakes. So this is kind of interesting. When I slam the brakes, would my velocity be positive or negative? Assuming that going forward is considered the positive direction and going in reverse is the negative direction.
It'd be positive.
It's positive, yeah. Because guess what? I'm still moving forward. I could still hit someone in front of me. Still moving. You're still gaining. You're still experiencing positive displacement. Now, what about my acceleration, though?
Well, you're decelerating, so it's
So it's
going.
negative, right? Because I'm losing. So it's quick. It's how quickly velocity is changing, and that's why we have this formula here. It's your final velocity minus your initial velocity over time. Now, if you so desire, if you set this equal to a, and you do a little like switcheroo, VF minus VI equals AT, VF equals VI plus AT. I stands for initial, F stands for final. Some people will do this because they don't like having so many subscripts. Just VI and V0 are the same thing. That's initial speed. Some people use V0 to kind of show like where you're starting. VF and V are the same thing also, final speed. So don't get confused by the nomenclature. They're the same thing. So that's another formula you can use that's really just simple algebraic manipulation of change in volume or change in time. And we're going to be working with that and doing another derivation of these formulas tomorrow. Is that let me do a different color here. Acceleration is a slope of a velocity versus time graph. Acceleration is a vector. If velocity and acceleration are in the same direction, the object is gaining speed. If velocities are in opposite directions, the object is losing speed. So again, we saw an example of losing speed when you slam the brakes. Anyone want to give me a good example of where you'd be driving and you're gaining speed? Like what would be a good time to do that? Not for
Going
fun.
onto the highway,
Go ahead.
like merging onto the highway.
Thank you.
Getting-
Thank you. Yes. You would be surprised. I'm a really chill, calm person. I tend to lose it when I see bad driving habits. I don't know why, but yeah, there's a reason why they give you the extra 500, 1,000 feet when you're going from a road to a highway. You want to go into freeway going at the same speed, right? You know, going the speed of traffic. So you really want to accelerate because it's very unsafe to enter a freeway at 20 miles per hour. You see that, and I was like, dude, what are you doing? You're going to get slammed and killed by a truck. So anyway, within reason, you know, don't go too fast. I mean, but that would be, yeah, because you're stepping on the accelerator of your car so that you can gain speed and then safely enter traffic at the speed that they're going, and of course merging carefully and giving yourself enough space, obviously. Now, if acceleration is constant, what's going to happen if you have constant acceleration? Velocity is increasing, right? So the graph of velocity is going to be linear. So if I have like velocity and time, and let's say initially my velocity is like, 10 miles per hour, then that's what I expect to happen. And the slope is going to be my acceleration, because remember, slope is change in y over change in x. And what's my y? Velocity. What's my x? Time. So when you have a constant acceleration, you're gaining speed. Now, because I'm gaining, velocity is increasing, what's going to happen when I do position versus time, it's actually going to be quadratic. The reason why the slopes of these tangent lines, what do the slopes of the tangent lines represent on a position time graph? Remember, if I'm doing slope, that's change y over change in x, or I'm doing the change in position over the change in time. What does that represent when you look at change in position over change in time?
Velocity.
Yep, because it's this displacement change in position, right? So the velocity is increasing, right? Because isn't the slope here kind of small, and then the slope gets way steep? So that's why it's going to be quadratic when you have constant acceleration. The there are some calculus principles that go into this. For those who have had pre-cal BC last year, I think it'd be a little easier to see that. I know many of you guys are still a year away from calculus, but I think just understanding graphically is good enough for now. Okay. So now we are going to look at this particular situation. I'll kind of give you a little head start here, and then we'll be working through these problems. So an object dropped near the Earth will accelerate downward at 9.8 meters per second squared. So we say it's negative because it's going downward. So we consider up to be the positive direction. We consider down to be a negative direction. I think that's fair. Because how are we defining position? The distance from the ground. So if you're going up, obviously you're gaining position, right? Going down, you're losing position. So all depends how you define the situation. If initial velocity is 1 meter per second downward, what will be the velocity at the end of 3 seconds? Is it speeding up or slowing down? Okay. So remember what acceleration is. It's a change in velocity over time. Well, my initial velocity is 1, so I want to find the final velocity. My acceleration, we say it's negative 9.8, and time is 3 seconds. Now remember the units here. So what are going to be the units for acceleration? It's right here, guys. So why is it meters per second squared? Why is it not just, if you have meters per second or seconds, how come the seconds don't cancel? Go on.
Because, well, it's almost like a triple fraction almost. It's where meters per second divided by seconds.
Yeah, you're dividing meters per second by seconds over 1, right? That's what we're doing. You're doing meters per second times 1 over second. That's why you get meters per second squared. So the units help a lot and understand what's happening too. To get a better quantitative feel, you really want to look at the units. So then I just solve for VF, obviously. So they have 3 seconds, negative 9 point. I don't even need the seconds here. Just get rid of that. So it's negative 27. Use a calculator, mind you. Negative 29.4, I think. Add 1. So, so it's definitely, so that's what happens. So my velocity is negative because we're going down, right? That makes sense. Okay. Can you hold on a sec? Sorry. Someone just had the front door open. Someone's playing music really loudly. All right. So now, how about this question here? What do you guys think? Are we speeding or slowing down? Well, think about it. What if someone dropped a baseball from an airplane and it's coming towards you? Do you think that baseball is getting faster or slower?
Faster.
Absolutely. And here's the thing. When velocity and acceleration are the same sign, you're always speeding up, even if they're both negative. If they're the opposite sign, they counteract each other, right? So when acceleration and velocity are opposite in sign, they're working against each other. Like when you slam the brakes, right? Because now the car's forcing you to reduce your velocity. So he's slowing down. Even if you go in reverse, if you step on the accelerator and go in reverse, you're speeding up, right? But then if you slam the brakes, like when you're pulling out of a parking lot, right? Ultimately, you want to do that because you don't want to, hit somebody. Then you'd be slowing down. Okay, so we're gonna do a little bit more practice. Before we do that, though, I kind of like to do number 4 with you guys here, and then I'm gonna do a little demonstration, which is gonna be pretty fun, and it's also we're gonna turn into a competition too. So let's see here for number 4. By taking the slope of the curve in the position time graph, verify the velocity of the jet car is 115 meters per second at t equals 20 seconds. Okay, so a little tough to do if let's say I had a ruler, but here's 20. We'll do green. So remember, that's gonna be a tangent line. That's what you're drawing here at a particular point. And then you're going, it's kind of hard to tell you. You have to pick kind of like another random point, like right here, let's say. And calculate the slope. So it's a total guess, So it's a change in y or change in x. So it looks like I'm doing 2,000 minus 1,500 over 5 seconds. Obviously, I didn't get 115, but I got close enough. So I'm okay with that. And then you could see that they're calculating all the different slopes. If I do blue. So for all these dots here, for every point, what does the y value represent? So for every dot on that second graph, because it's a pair of coordinates, x and y coordinates, represents blank from the position graph. So what does every what does every y value represent on the second graph in relation to the first graph? What did we just do in the first graph? So I'll call on someone. Go ahead. Oh, someone's going to talk?
The speed.
Yeah, well, velocity.
Like
We're doing velocity, but what did we do in the first? Like when I drew this green line, what is that? Why did I draw that green line? What was I trying to find that green line?
the slope
Right. The slope of what?
of the position against time graph.
But more specifically, the slope of which? What was I calculating the slope of?
Of the speed.
But how did I get that though? Like, what did I first have to do? How did I find the slope?
Oh, you found the displacement, right?
Right, which is change in y over the change in x, which is slope, but of what line? Of the tangent lines. So I'm going to do the demonstration next because I think that will really help drive this point home. For every point on the velocity time graph, the y value represents the slope of the tangent line from the position graph at each x value. So for example, let me go and clear this. Let's take a look at 10, x equals, or t equals 10. What's the y value there? What'd you guys say? Anyone can chime in.
60.
Yeah, we'll say 6. Yeah, maybe my drawing's not the greatest. We'll say 60, sure. So that's going to be the slope of the tangent line at x equals 10 for the position graph. Okay, now let's look at x equals 10. Let's draw a tangent line. Let's put kind of another random point, like maybe off here.
Sorry, what does that say? Slope of something?
Tangent line.
Gotcha.
Yeah, tangent line. That's, yeah, I should have wrote that more clear because that's the most important thing. That's the whole point of this. Yeah, so if I draw a tangent line, meaning it touches at just at x at t equals 10, and I identify one point here, like say 10, 500. And let's say identify another point, I don't know. We'll say 20, 1100. If I find the slope, I get 610, which is 60. So that's how you create these graphs. Is you're purely taking the slope of the tangent lines and then reporting them as y values for the velocity graph. This demonstration, I think, will really drive this point home. And then I'm going to let you guys get to work on some of this stuff. And I'll hop into the breakout rooms to help you guys out with this. Okay, so now let's actually go to this here. And this is going to be the fun part for today, because we're going to turn this into a competition. And if anyone can beat me, I will let you watch that video I was talking about when I was dancing with a flamenco dancer in Spain many years ago. Let's see, there we go. Okay. So don't worry about the word derivative. That's a calculus thing. So, but here's what's happening. Think of this as, so the solid curve, think of this as a position graph. So that's position, and here's time. Okay. Now, what I'm going to do, the one that has all the dots on it, that's going to be my velocity graph. So we're going to break stuff into segments. So I'm going to cheat a little bit. Okay. Because someone explain to me why I chose that color coding. What's happening in green, what's happening in red?
It's going up in green and it's going down in red.
Good. Now, in the green part, is the velocity positive or negative?
Positive.
The red part, is velocity positive or negative?
Negative.
Good. Outstanding. So for my velocity graph, the y values will be the slope of the position graph. So clearly, if I drew a tangent line here, the line I just drew, is that a positive or negative slope? So Rahel, is that positive or negative? I'm just gonna start cold calling, sorry. So Rahel, is that positive or negative slope to the line I just drew?
Negative.
No, this one right here?
Oh no, that's positive.
Why is that positive?
Because it's velocity positive.
Right, but also is y increasing or decreasing as x increases?
It increases.
Exactly. Y is changing in a positive way. Now let's look at this next line here. So Kate, I'll call on you because you're the next person I see. So that line, the second line I just drew, does it have a negative or positive slope?
Negative slope.
Exactly. So now what I'm going to do, I'm going to kind of get rid of that because it's a little distracting. I'm going to take this dotted curve here, and I'm going to move it in such a way so that the y values represent the slope of the positive graph. So I need this dot here to have a positive y value. It's hard for me to tell exactly what the slope is right here, but it seems like it's probably about 2 or so, and it's getting a little bit steeper. But then it's not getting as steep over here. And then what would you say what my slope would be? Let me shine a spotlight on it. So right here, what would you guys say what my slope would be at the peak? Steve, what do you think? What was, or yes, actually, I'll call on Steve. Steve, what would you say my slope would be at the peak here? Go ahead, Steve. Steve? Okay. Steve, what would you say my slope would be at the peak here? You're muted.
Sorry, got distracted for a second.
No worries. So what would you say the slope would be here at the peak? If I drew a line here that touches the peak at one place, what would you say the slope would be?
Wouldn't it just be 3?
Well, no. That's a y value. I want the slope.
It'd be 1, right?
Well, let's draw it. If I draw a line here, it's a horizontal line. So now, what would you say the slope of that horizontal line would be?
Oh, it's 0.
Exactly, good. It's 0. So what's going to happen, I'm going to move this curve down here now because I want it to be 0 right there. And then it starts getting negative, right? And it starts getting more negative. The slopes are more and more negative. And then it's starting to get a little bit more positive. Then it's back to 0 again at the bottom part. And now my slopes are positive, more positive, then kind of back to 0. Then it's definitely negative here and very, very negative over here. So I'm going to go and clear this, check for my accuracy. I could do better than that. If you see the actual results, you can see I was pretty close. So this is going to be the competition. I'm curious to see who can actually beat my score here. So that's something I'm going to have you guys do in your groups. Not now, but maybe after lunch we'll do that. For now, I want you guys just doing a little bit of practice before we break for lunch, because this is going to help you get a good feel for how to draw tangent lines from a position graph, and that's how you will generate the velocity graph. This is something we actually do a lot in the beginning of calculus. We do stuff like this. I'll do one more so you guys can see, because I know I could do better. Okay, so right now my slope is positive, but then it hits 0. Then my slopes are negative for a while. and back to 0. Then it's positive. Then back to 0, kind of like that. And kind of negative. Okay, good luck in being that score. That was pretty good. You see I'm pretty accurate there. So basically what I'm doing is I'm drawing these tangent lines. I'm trying to figure out what these slopes of these tangent lines are. Like I know like these tangent lines over here are all negative. So that's why I have like all these dots here with negative y values. And then I know that the slopes are 0 here and 0 here. I actually had an easy graph. So that's what I'm trying to do there. So here's what we'll do for the next 15 minutes before we break for lunch. Let's go back to this. Let me actually reset that graph. Okay. So I'd like you guys to work on 1, 2, and 3. So number 1, you're going to do a velocity time. Well, actually, yeah, you're going to draw a velocity time graph. So we're going to have to do a sketch of that. Number 2 is just more kind of answering that question. 3 is using this data here. 4 I kind of did with you guys. 5 I'll try. We'll kind of do 6 or 11 a little later. But for now, we'll just have you guys do 1, 2, 3, 5. And if you get a little bit more ahead, that's fine. So I'm going to put you guys in breakout rooms again. So you guys do the 1, 4 work. And I'm going to come and check in on you guys and kind of give you guys a little push here. We'll make these a little bit bigger, these breakout rooms. Maybe we'll recreate, we'll do 3. Yeah, so we'll do 3 rooms. And we'll set the timer for 12 minutes, 60 seconds. Okay, and I'll hop into one of the rooms right now. Justin, you can join one of the rooms. Hey guys. Okay, so let me share my screen and I'll help you out with number 1. So you're throwing a ball up in the air and then it comes back down, right? Mm-hmm. So initially, the velocity is going to be positive because it's going up, right? So you want to consider up to be the positive direction. Mm. Great, my computer froze. Hold on. Come on. Yeah, up. Oh, it didn't freeze. My stylus is dead. I need to charge it. Good thing we have lunch break coming up. So up is going to be positive. Down is going to be negative. Okay. So you throw it, and there's going to be a surprise some. You know, initially, the ball's at rest. We'll say that. So it's going to be positive, but then eventually it's going to come back down. And this is going to have a negative velocity until it kind of, until you catch it. Actually, probably more proper if we did it like this. We'll say, you know, there's some initial, because obviously there's initial velocity because you are throwing it up. So kind of would do that. So this is basically when it hits its peak. Because if you throw a ball, say you have a person here, right? You throw a ball, what's going to happen when it hits its peak?
It's like in between going up and down.
Just momentarily stopped, right? For a brief moment, it's kind of motionless. And then, but now you're going down, so that's why you have a negative velocity. And describe the graph. So you can kind of call this like actually your vertex. And that you can actually call like your initial speed. So that's that one. And then for 2, so we could, how can you use position time graph to find constant? So what you'd want to do is, you know, you'd have something parabolic like this. That's position, that's time. So you could say, slope of tangent lines. Provide velocity values. And then from there, you take the slope of the velocity graph. Because you're going to make the velocity graph from the slopes of the tangent line. So you could kind of think of it this way. That's me time. That's me position. And that's me velocity. And then once you make your velocity graph, then you take the slope again. So that's what you would say for number 2. Now for 3, all you're doing here is taking the slope. So what would you say the slope would be for this first portion here?
2/1.
How about over here?
0.
This we kind of have to guesstimate a little bit. Looks like the change in y is 40. The change in x is about maybe 12-ish. So close enough, 3.8. So it's a rough estimate. So I'll have you guys keep working through this. And then we'll meet back in the main room in a few minutes. Any questions? Okay. Stop sharing, I'll leave this room. Hey guys, how are we doing here?
I'm good.
So really quickly, for something like number 1, we probably want to do, well, first we have a person throwing a ball up, right? And then it's come down. So the ball goes up and comes back down. Now let me ask this question. When the ball's at the peak, what would you say is happening with the velocity there?
It's at rest.
So 0, right. And you're doing a velocity versus time graph. So probably halfway through, you're going to have something like here. Now, when the ball leaves your hand, it's going up. And remember, we consider up to be the positive direction. That's intuitive, hopefully. And down being the negative direction. So when the ball leaves your hand, would you say the velocity is positive or negative?
Positive.
Positive, good. Now, right before it hits the ground, because it's going down really fast, would you say it's negative or positive when it's going down?
Is
So
it still positive? Because it's.
Well, it's speeding up, but the things that because it's going in the downward direction,
Oh, gotcha.
it's negative. Remember, that's why velocity is all about direction.
Okay, yeah.
So your graph for number 1 could look like this. Something like that.
Okay.
And that's going to be your vertex, the x-intercept. And that's going to be like, you know, initial and final. So that's how you can kind of draw that for number 1. For number 2, do you guys have ideas, or do anyone have anything down for number 2 that they want to share?
I think I have. Oh,
Yeah, go ahead. What do you got?
so I said that you would just find the slope
Mhm.
of the tangent line at a
Yep.
given point on the graph, and then you would just graph that as the y value, and then find the slope of that coordinate.
Got it. Yes, you do the slope twice. Very good, Brandon. So you want to do the slope of position graph to make the velocity graph. And then do the slope again. Right. Because that's the whole point. It's all about slope. Sorry, my handwriting sucks here when I'm using the mouse. Not like as much about the stylus, but then do slope again. Right. So again, for 2, you say take the slope, make the velocity graph, and then when you have velocity graph, take the slope again. For 3, so because you have a velocity time graph, you want acceleration, you're doing slope again. So what will be the slope for that first segment? If you do change in y over change in x. So what's the change in y for the first, for A? Jonathan, what do you think? What's the change in y for the first segment?
Well, it doesn't go from 0 to 40.
So it's 40, good. And what's the change in x?
20.
Good. So what does that divide to?
2.
That's it. That's what you get to. Perfect. That's all you gotta do. So don't overcomplicate it, because that's what acceleration ever is. It's just a change in velocity over time. So you can see why the next one would be 0, because there's no change in y. So numerator is 0. For C, you kind of have to guess the change in x a little bit. Maybe it's like 11 or 12. The change in y is probably 40. So you get 3.8 as an estimate. We'll probably break for lunch in about 5. I'm actually going to keep the rooms open. So we'll probably take a break in about 4 or 5 minutes from now. But go and try like 5 and 6 perhaps. And then we'll be in the back in the main room. Hey guys, I'm just keeping the breakout rooms open for a couple more minutes. I want to check in with you guys. So how did number 1 go? Or do you guys have any questions about it?
I guess the only question I have is on number 2.
Okay, so for number 1, first of all, if you have a person throwing a ball up in the air, right? Like that, right? When you're at the peak, what would you say the velocity is going to be at the peak there?
0.
Yeah, because at rest. And the velocity is positive beforehand and negative beforehand. Because remember, we're considering up to be the positive direction. So we're keeping this very intuitive. Up is positive direction, down is negative direction. So your velocity is positive, but it is losing velocity until it reaches its rest. And it's negative afterwards. So this is going to be your vertex. So the x-intercept of the velocity graph is the vertex. So that's kind of a key thing. X-intercept of a velocity graph is a vertex of position graph. That's because they're tangent lines, right? And that when you have a tangent line drawn right here, that's a 0 slope. And y, remember, slope is change y, change in x.
Wait.
And that's change in position over time. So the x-intercept of the velocity graph is a vertex of the position graph.
Should the vertex, not the vertex, but shouldn't the graph come back to 0 though?
Yeah, it does, because it does stop. Yes, and that becomes a piecewise function actually, because it's right before it hits your hand. It's coming really, really fast, and it instantly. So you could think of it kind of like a very sharp. But right before it hits the ground, we kind of keep it like that. This is right before it hits the ground. And this right here, of course, is your initial velocity. So I think I kind of dissected that one to death. So let's look at 2. So first off, if you have a position time graph, if you take the slope of the tangent lines on the position time graph, what kind of graph do you generate from that? And Isaac, I know you're asking that question. So if you have the position time graph, and if you take the slope of the tangent lines, what does that get us? Are you muted?
Pardon, could you say that one more time?
Yeah, if you have a position time graph, and when you take when you draw the tangent lines and you find the slope of those tangent lines, what does that give us?
Acceleration.
Velocity, no, it's velocity.
Sorry.
Remember what is velocity? Change in position or change in time, which is slope. Because the position is the y value and the time is the x value. So now you have the velocity graph. Now when you have the velocity graph, what if you do the slopes of the tangent lines again? Where does that get us next?
Acceleration.
There we go. So you got to do the slopes of the tangent lines, make it a graph. So let me type this as this text here. Slopes of tangent lines of position graph to make velocity graph. Then slope of tangent lines of velocity graph to find acceleration. That's how you do it. So let's look at number 3, right? So for number 3, so what's the slope going to be for that first segment there for A?
1.
Well, not quite. I see why I'm saying 1.
2.
Yeah, because you're going up 40 and right 20. I know. I can see why I said 1, because you go up 2 boxes and right 2 boxes. But you got to look at the units, right? What would you say the slope would be for the second part?
0.
Right. And then the next one, you kind of just sort of have to guess a little bit. Like the change in x is about 11 or 12. The change in y is about 40. So they get about 3.8. Close enough. Yeah. So we're going to explore this more when we come back from our break. So I'm going to actually have everyone come back to the main room really quickly. So let me end the breakout rooms. Can you close the door, please? Can you close the door, please? Thank you. Okay. We're waiting for more, the people to come back in. Don't know where the other group went. Oh, they'll be here soon. Okay. Okay, still waiting for 2 more people to come back in. Okay, not sure who the 2 people are, but anyway, so really quickly, let me just recap what we're seeing here, and then we'll have a break and we'll do a little demonstration. So remember, velocity is a change in position over a change in time, or just say just time in general. So if you have a position graph and you have time, and say you have something kind of like that. Well, actually, let's do something more simple. Like that, right? Now think about it. Your position is y. Your time is x. What does change of y or change of x represent again? Mathematically, what's change of y or change in x for a line?
Slope.
Slope. There we go. Great.
Slope.
That's why we care about the slope of tangent lines. Now, when they get a little bit weird and when they get more curved, that's why you got to do tangent lines, right? I mean, this one's easy. I could find the slope of that, right? That's not hard. A little bit more tricky here. That's why you got to draw tangent lines and estimate them. And then lastly, acceleration is a change in velocity over time. So if you have a velocity graph, so that's v and t, and we'll kind of draw it the same way again. Again, change in y over change in x. So again, you're looking at slope. So we're going to explore this again when we come back from the break. So we'll do a 30-minute break. So we'll have to come back at 12:10. We'll do that demonstration I showed you. We had to draw the new curve based upon tangent lines from the original curve. We'll do that, and you guys will be in groups, and I'll kind of come and help you guys, and I'll kind of enable screen sharing so I can kind of guide you through it. And we're gonna see if anyone can beat my 93%. So hopefully this will enable you to get better with this stuff. And then we're gonna do a part of the lab later today, and then if we have some time at the end, we'll kind of finish up this 1-4 classroom. So we got a lot still left to do, but I do promise you we'll be done by 1:30 today. So cool. Just take a 30-minute break. You can just stay on or turn your video off, or just leave and come back. I'll leave the room open. Yeah. So I'll see you guys in 30 minutes.
Actually, it's not so bad for not, but just so we have one door open first, that really all the noise from the neighbors. That was the only problem. Yeah, there was like a lot of music, like, I'm happy, blah, blah, blah. That's what I think. Sure.
Well, what is it?
I also do
Well, I never, aren't you the greatest little question ever?
Now you don't hamburgers or chicken nuggets?
actually, do
gotta miss, we gotta buy this bottom, this. So that's a hippopotamus. Oh, that's the only one. He was there the whole time, but they just didn't see him. They didn't see him. See if he can stop it.
No, well, the seed is
He needed to run there.
Yeah.
He took it.
So that's the Home Depot.
Is that when but collision place, the collision system?
Probably.
So we just need a hardware store.
The Home Depot was easy.
We need a few things to Home Depot anyway.
What else do you need from there?
More shelf liners, light bulbs, and air filters.
How was laundry transfer?
Just like
A lot to go after 4.
Vampire bats. All these things in the food. But, wait a minute. You don't have that hippopotamus. Well, of course I have. I'm right this way. He's by our website every day. Says, this way to see him later this time. Yeah, he's gone. Don't you worry, Don. We'll spread out all the time. Papa, because he needs your car moved so that you can get your car.
Yeah. What's your first one?
Right, how would that? So you don't get into all the car now?
Oh.
Did you park this?
Yeah, I mean, it's a school field show us with my team. Yeah, it was small.
Oh, this one.
Do you think they're really showing?
Well, you for barbecue Sunday.
Yes.
It's gonna be the hardest. Okay, I'll be back.
Actually, my car.
They just walk by him. You didn't see him. I got a miss. I knew that I could spot a miss. What do they all say? Not a hippopotamus. Off we go then. Come on, man. Excuse me, miss, I think I see him. That's what Liam is saying. And he says, off we go then. Come on, Liam. Says the teacher. Would you put in proper miss? We'll find that hippopotamus. We're here, the most superior hippo hunters in the area. I see him, miss. He's on the ground. I'll get him while he's snuffing around. What's that? Yes. Got him, miss. I got him, miss. I got him by his trotter. A trotter? What's a trotter? You know what he calls his leg a trotter? Because when his Norfolk runs, he trots. He goes, and he's grabbing his leg. He says, this is the leg that trots makes him trot. Trotter. This is your trotter. I'm not a hippopotamus. Okay, so now the next page is, oh, children, quiet, Leo. But excuse me, miss, I think I see him. Is he hippopotamus? We a hippopotamus? You're the greatest band of hippo hunters in the land. See him, miss? He's very good. I'll chase him with my 20 step. Can you see pictures of them? No, they're not on the trail at this moment. No, look at this boy doing. On top of this boy, on top of this boy, and you look. I got him this. I knew that I could stop him this. Hey, look. What did you say? Yes. What? What's this one? You can choose it. Is that a hero too? Two hippos. Oh my. Oh my goodness. Oh. You see one, but look at the eyes on it. What do you think? Is it a hero maybe? Is it an elephant? Let's see. Let's see. You think so? Let's see. Turn the page and see. Oh, there's a nice chameleon and a snake. And this is like a gecko. There are a lot of things in this. Yes. Well, I like this turtle a lot. Yes, yes. Now off we go. Be quiet, Rhiannon. Look at this. He's super not trying to teach you. Excuse me, miss, I think I see him. And missing hippopotamus, the trail's getting hotter, miss. Good thing you're here, the very best. Nope, he's in this page. But Leanne said he's over here. Yeah? The trail's getting ominous. Good thing we're all here. The very next will take over. Yes. I see him this time on his trail. I'll grab him by his shirt. I got him this. I got him. He still wants to be watching this. That's not it. That's excuse me, miss. I think I see him. Come on, children. Look at Lena. Look at Lena. Look at he's listening to Lena. Lena's right at the water. I think that's maybe a shark. Or no, it's a manatee. Something like that. Let's check and see. Good thing we're here for all this work as hippo hunters. I see him, miss. I see his fist. I see his fin. Watch me, miss. I'm diving in, she says. That's me. I was straight apart. She'll find that. People all get for it. Let's get the wipers on the air. But it's not. It's a I don't see that. Maybe he has it on the back. Yeah, he's using it on the back. Maybe in the same fish tank there's a shark. Maybe there's a shark in there too with the manatee. I like manatees. They're like hippopotamuses and elephants in the water. You ever seen a manatee? Someday we'll go to the San Francisco Prairie and they have manatees there. It's a very big animal in the water. It's an animal. Now, stinky hippopotamus, what kind of bother this? She's ridiculed a lot of us. And yet they're all upset. They're upset because they didn't find any hippopotamus. Nobody's going to say, oh, nuts, we have to go home and see a hippopotamus. Only go in, fingers crossed, that really hippo isn't lost. But excuse me, miss. What is it, Liam? Excuse me, miss. The hippo, miss, I really see him behind there. Aren't you clever? The greatest hippo. And that is really even the zookeepers looking at this like, yeah, let's turn the page. What do we see? We got him, miss. We got him, miss. We got him by his bottom, miss. So that's a hippopotamus. So that's a hippopotamus. On the family. And all the children are grabbing him. They're so happy to see him. Hello, hello. Teacher says, so that's a hippopotamus. Maybe she's never seen one. Work on and I thought, so you're happy. Okay, oh, they all get to ride with us. Hey, I like your shirt. It was wearing that line shirt. Shirt that looks like it comes from the water. It was in the water. I don't think so. It was a hat. So many kids, let's come and many kids can write on it. I'm talking to, he is such a big one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 17 kids. Holy mackerel. I love this so much. I know. Where would you like to write? Where would you be? Right on his nose, on his back, by his eyes. See, there's big gummies in the front. And you're walking with my daughter. You could take him on a leash. He's too big. Too big for a big leash. You need a really huge leash. The biggest leash you could have. They're very big. If you look, should be inviting to come to support students. The companies are long. Then he would just swing and splash. He might say, how do I get out? He can be to use the stairs. And the ladder would break. And then the statue. And then we need a crane. How would we get a crane with that door? Uh-huh. Or if he's, or if he puts his eyes on the land, I can grab his eye. And then pull him up. You think so? Because things are not as heavy in the water. Did you know that? That's true. That in the water, things are not so heavy. We can look up the heaviest thing in the water, but if you're outside the water, no, too heavy. So we maybe couldn't even lift that head up under the water. But once we get in the land, no way, too heavy, too heavy. I see the other. Would you like to see the other? Whoa. You see that? Okay, there you go. Yeah. Oh, what's that one? I got this, I got this. I knew that I would spot this. Stop it! You go harder. That's a secret. Amazing little colors in the old secret. Oh, look, he's in the old glass. He says, I can see. No, it isn't. He would definitely get that song. He would. Yes.
It's not all forwarding the email.
It's either you or percent.
But you're happy now?
Yeah.
Oh, okay, you're good.
Then they have it. Look, do you have a copy of the American Home Shield
Contract.
contract?
Yeah, I'll email it to you.
If you get that for me, let me take a look at it.
Sure. Yeah, I think it really comes down to repair versus maintenance. And they do, you know, the home warranty covers repair, like if there's a broken piece, or if you have to replace the whole unit. Maintenance is more like, okay, cleaning, freon. That's maintenance. I don't think that's covered.
That should have been taken care of by the previous owner, I think. I think they screwed you on that.
Well,
they didn't screw you intentionally, it's just that they didn't want to spend the money to have something.
I mean, we gave the other people a brand new air conditioner.
You went way above and beyond.
I mean, $3,000.
Yeah.
Granted, it was broken several months before. You didn't say that.
Yeah. Well, you did the right thing.
Yeah, but we knew we were gonna.
And at clear conscience, you couldn't stick something.
No, but I'm not sure if Chris told you, they, the new owners tented the house.
They what?
They tented.
Oh, really?
Termites.
Did they discover termites?
No, the report didn't show it. No. So, but there was some drywall in the garage that we never got around to addressing, but we didn't have to. But anyway, maybe just for a peace of mind. I don't know. But I'll stop. It don't matter. Yes.
That's expensive. That's
Yeah. Oh. That's not, we did it once.
Yeah. Crazy. Hey guys. Guys. When you're ready. When you're ready.
Yeah, I feel like it's the same ones we got. I have a question about it.
It must be yours. But you did that before, so you're nicely.
Well, I thought it was just myself.
There's a stream. I go there to see the big. Yes. you know, like a cedar that we saw those in mountain. They kind of go like this. That's how they swim. Sometimes the ducks can.
Here we go,
Or you're gonna go to Home Depot. Check and see what's out there.
yeah, those are the ones we got.
You're gonna get two. You're gonna get two here. Let's check and make sure that you got clearance. This is small. You're getting tall. Oh, yeah. Yeah, you got plenty of space. Yes.
Oh, you gotta be kidding me.
Except because you know,
You should.
Jen's bathroom, we had a counter in the back. I had to make sure.
For that this year.
This one's okay, it's got plenty of space.
Chris just texted. Well, that's not here today. Kate just called and said, we're still on the show in Florida. Very soon, Chris, Chris will go. We'll have to reschedule for 2 weeks from now.
Bill and Gus?
Yeah,
Bill and Gus?
yes.
Chrissy just said.
Oh, I know, I just read it.
Oh,
2 weeks.
no pool fence today. Oh, my goodness gracious, that is so nasty.
Well, you gave two or three things.
Yes.
If you go left, the only thing you're gonna go up for is the filter. Or you gonna,
Well, she needs liner and holes. Home Depot?
yeah.
No, probably no rush now. So,
Oh, yeah, I was gonna say, I can go up.
well, if you don't mind, if you want to go to the university, if you want to do that.
That's what I'm asking, what do you need, the filters?
So the filters, remember the same liners we had that we bought?
Say, liner, what kind of liner?
The clear liner for the shop.
Oh, right.
Remember, we bought that.
Yeah.
You want to get this phone? She'll tell you. Yeah, so it's like this liner. Yeah, if you want to get this phone, she'll tell you exactly. Yeah, that's right. I don't know if I will like the show.
Actually, you know, she's in the back. The guy's gonna come.
So what's your way? That way, yeah.
Okay. I'm gonna sit outside there.
Okay. Okay, guys, looks like most of us are back. We got 10 people, so we need about 3 more we're waiting on. Actually, let me stop this recording. I can't believe I recorded during the break. I'll start a new one. So let me stop this recording.